This lesson is on Riemann sums and definite integrals. A Riemann sum and actually the value of a definite integral are two ideas that we touched on back when we did the summation, back when we found the area under a curve. Now we're going to formalize it with some vocabulary, with some definition and some notation in this section. So we have a Riemann sum. Riemann was the name of a mathematician, and he developed this method for estimating the area under a curve. And so it's called the Riemann sum, and it's where you use rectangles to estimate the area under a curve, between the curve and the x-axis. So it's an estimate, and it's found by using rectangles, and the rectangles can either be equal width or they can be different widths. If you're using rectangles to estimate the area under a curve or between the curve and the x-axis, then you're finding the value of a Riemann sum. A definite integral is the exact area between the curve and the x-axis. It gives you the exact value. So the definite integral is going to be the exact value of the area between the curve and the x-axis. There's a little bit more to this, just say on the next slide here. The notation for a definite integral is the same as an indefinite integral, except you're going to have limits of integration, an upper limit and a lower limit. So this is red. The integral from a to b, so your starting value and your ending value, the integral from a to b, f of x dx. What this means is the area under this curve, f of x, between this curve and the x-axis, from this curve, and this dx tells you between the x-axis, between x equals a and x equals b. You could also find this on the y-axis, so you would have an f of y and a dy, and these would be going on the y-axis. So this dx tells you which axis you're taking the area with respect to. The majority of the time, it's with respect to x, but if you saw this all in terms of y, then that would be between the curve and the y-axis. So that's something to keep in the back of your head, because you do see a few problems like that down the road. But for this problem, under this curve, area under this curve, with respect to x, between x equals a and x equals b. So the area from x equals a and x equals b, those two vertical lines between the graph of f of x and the x-axis. If you have an area that's underneath the x-axis, you have a curve that's below the x-axis, that area, or the value of that definite integral, is said to be negative. So you would still find the area, but the value of the definite integral would be a negative number. Area under the x-axis is defined as a negative value when it comes to calculus and definite integrals. Key thing to remember here, indefinite integrals a couple sections ago was asked you to find the general antiderivative, the equation. When you antiderive it, what's the equation? You threw your plus c on the end with that constant, because it could be any equation, or that equation with any constant at the end. A definite integral, when you have limits of integration, when you're finding the area between two x values, or two y values, is going to be a number. You're going to get a number, a numerical value for your answer. This is asking for an area, so you're going to get a number, a numerical answer, a value here. So let's look at a few examples here and see what it means geometrically. Definite integral from -2 to 1 of 2x with respect to x. So we're going to find the area between this curve, y equals 2x, and the x-axis between x is -2 and x is 1. So you see, y equals 2x, or f of x equals 2x, diagonal line. X is -2. X is 1. Remember, it's between the curve and the x-axis. So we're just going to use a simple geometric formula to evaluate this definite integral. And we're going to break this into two triangles. From -2 to 1, we have this area in here, the area of this triangle. And from -2 to 0, we have this area of this triangle. And from 0 to 1, we have the area of this smaller triangle. So we have 1/2. Base times height for the area of this. So 1/2, base is 2, height is 4. This was 2x. So the base is 2, the height is 4. 1/2, base times height's area of a triangle. But because this area here is under the x-axis, we're going to throw a negative sign out there. So this area here is a 4. This triangle here has an area of -4 in terms of the definite integral definition. Over here you have a base of 1, a height of 2. So 1/2 times 1 times 2 would give you 1. And since it's above the x-axis, it has an area of +1. So -4 and +1 would overall the value of this definite integral would be -3. Let's look at another integral here. The area between x is 1 and x is 3 of the graph y equals 4. So you graph y equals 4. You have your horizontal line at 4. 1, 2, 3, 4. So you get x is 1, x is 3. So again, we can use a geometric formula to find the value of the definite integral. It's above the x-axis, so it's going to have a positive value. Base is 2, height is 4, so the area of this rectangle is going to be 8. So the value of this definite integral is 8. So far, we're using definite integrals. We're using geometric formulas to find the value of definite integrals. In the next lesson, you'll learn some shortcuts or some rules to find the value of definite integrals are a little more complicated. But it's important to understand what this is asking. That's why we show you this first. You see the curve. You see the limits where you're going between, and you find the area so you understand what it's asking you when we get some application problems in the next section of the section after. Again, area between this curve, x plus 2, and the x-axis from x is 0 to x is 3. So you graph y equals, or f of x equals, x plus 2. Y-intercept of 2, slope of 1. So I'm going up here. Now your area between the curve and the x-axis is a trapezoid. So you're going to use another geometric formula. 1/2 average of the bases times the height, area of the trapezoid. So 1/2. Now remember, with a trapezoid, you're used to seeing a trapezoid with parallel bases at the top and bottom. But here our parallel sides are left and right. So these are actually the bases of this trapezoid. So it's going to be 1/2. The base is going to be 2 here. It's going to be 5 here. So 1/2, 2 plus 5. You average the bases and multiply that by the height of the trapezoid, which in this case is the distance between the bases, 3. So average of the bases times the height, you get 21/2. So the value of this definite integral is 21/2 or 10.5. One last common geometric shape where you're asked to find the value of a definite integral is going to be a circle. The area between square root of 4 minus x squared with respect to x, between x is -2 and x is 2. So this is the equation for a circle centered at the origin with a radius of 2. So you see your semicircle there. Remember, if this is a function, this has to be a semicircle. We're looking at the top half of the circle. So we're going to use a geometric formula, the area of the circle, to find the value of this definite integral. Well, the area of the circle is pi r squared, but since this is a semicircle, we're going to have half of that area. So 1/2 pi r squared. The radius of this circle is 2. So 1/2 pi r squared gives you 2 pi. The value of this definite integral is 2 pi. Above the x-axis again, so it's a positive number. A couple special definite integrals or definitions they want to give you here. The integral from a to a of f of x dx, meaning the area between f of x and the x-axis, between x equals a and x equals a, is 0. That should make sense. You're not moving. X is the same thing. There is no area. So that's why from a to a is 0. Special case, they might try to trick you sometimes. Another definition of a definite integral, or involving definite integrals, is the integral from b to a of f of x dx is defined as the negative integral from a to b of f of x dx. So the value of the integral from 1 to 5 of f of x dx was 12. Well, then the value of the integral from 5 to 1 of f of x with respect to x would be -12. So if you switch the limits, if you reverse the limits, then you're going to reverse the sign of the integral, or the sign of the value you get from the integral. Here's another property of definite integrals, and we're going to apply it to a problem here. The integral from a to b of f of x dx is going to be equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. What that basically does is that gives you a point c. So the value of a to c, then from c to b. So you kind of split it into pieces. So the overall integral from a to b is the value of the integral from a to c plus the value of the integral from c to b. And we'll use an example here for you to see that. The integral from -1 to 1 of the absolute value of x with respect to x, the area under that curve or between that curve and the x-axis. Well, absolute value is really two functions. It's really a piecewise function that has two parts. It has the part that's coming down, the negative part, and the part that's going up. So whenever you have an absolute value equation, you want to split the definite integral where the absolute value, where the two pieces split, where the vertex of that absolute value function is. So this function is pretty simple. Absolute value of x, the parent function, is going to split at 0. So I'm going to write the definite integral from -1 to 0 of negative x, because it's the negative version of that absolute value function, plus the definite integral from 0 to 1 of positive x. And that will give me the overall result. I split from -1 to 1 at 0. So from -1 to 0 plus from 0 to 1 will give you your overall value from -1 to 1. And you can see, you would find the area under this curve, 1 by 1 by a half would be a half, 1 by 1 by a half would be another half. So you would have an area of 1 overall. This is just using those geometric formulas, area of a triangle. The main thing to see here is you can split absolute value functions. You can split any definite integral, but absolute value functions are ones where you almost always have to split if that vertex falls between your upper and lower limits of integration. Okay, two last properties that we're going to apply, and then that's it for this lesson. The integral from a to b of k times f of x dx, meaning some number, some scalar multiple of that, something multiplied by the function, is equal to that number pulled out in front times the definite integral, times the value of the definite integral. So if you know the value of this definite integral, and you multiply the function by some number, then you take the value of the definite integral and multiply that value by that same number, and that'll be the new value, the new area between the curve and the x-axis. And also sum and difference of definite integrals. The integral from a to b of f of x plus or minus g of x with respect to x can be broken into pieces. The integral of f of x from a to b plus the integral or minus the integral of g of x from a to b. So you can break a string into separate pieces. And we're going to see both of these applied in this next example. We're going to break it down into pieces, and we're going to use the scalar multiple idea. So they're going to give you, they want you to evaluate the definite integral from 1 to 3 of negative x squared plus 4x minus 3 with respect to x, if you're given. So they're going to give you some information. The value of the definite integral from 1 to 3 of x squared with respect to x is 26/3. The value of the definite integral from 1 to 3 of x with respect to x is 4. And the value of the definite integral of dx, of 1 dx, from 1 to 3 is 2. All right. A lot of people see just the integral of dx and get a little confused. If you have to, put a 1 in front of it. It's just like 1 dx. You don't write 1 dx just like we don't write 1x. You don't write that coefficient of 1. This is just the definite integral of 1 dx. So, we're going to break this into 3 pieces. We're going to break this into 3 pieces using that sum and difference rule and pull out the factors. That scalar, that k. So here I have x squared. squared. So I want to pull out a negative 1 and write the definite integral from 1 to 3 of x squared dx. So I pulled that negative out front. Then I want to add my next definite integral. Well, I know the definite integral from 1 to 3 of x dx, so I'm going to pull out that 4. So it's going to be 4 times the definite integral from 1 to 3 of x dx. Then I want to minus 3. So I'm going to pull out the 3 from the integral from 1 to 3 of 1 dx. Dividing 3 by 3 gives you 1 dx. And now you use these 3 given definite integral values and apply. This whole thing here is 26 thirds. So I start with negative 26 thirds. Plus this whole thing here is 4. So it's going to be 4 times 4. Minus this value here is 2. So it's going to be minus 3 times 2. So I get negative 26 thirds plus 16 minus 6. And you end up with an overall value of this definite integral. The area between this curve and the x-axis, between 1 and 3, is going to be exactly 4 thirds. So remember, definite integrals give you the area between the curve and the x-axis, or the curve and the y-axis, depending on what that variable of integration is at the end. It's going to give you a value. When you see limits, your definite integral gives you a value, a number. Riemann sums, we touched on in the previous lesson, where you break it down to rectangles and estimate the area, and we actually use that limit or use the limit as the number of rectangles went to infinity to define the exact area under a curve. And then in the next lesson we do, we're going to put all that together, applying definite integrals, indefinite integrals, Riemann sums, and the summation. Put all that together and develop what's called the fundamental theorem of calculus that ties everything you learn together so you can do these problems a little bit quicker and do a little more complicated problems as well. But every piece is important. Knowing what an indefinite integral is, how to antiderive, knowing the summation idea, knowing how you're using the rectangles and the Riemann sums and adding up the area of rectangles, and then knowing what the definition of a definite integral is as the exact area, and learning all these properties of definite integrals. And then once we have these 3 pieces together, then we'll tie it all together in the next lesson.